Welcome to lecture number 8 of the Power System Protection course. In the last lecture, we discussed about the fault analysis. In fact, the fault analysis is very useful in designing the protection schemes. So, already we have seen various kinds of fault analysis in the last lecture. We covered mostly the unsymmetrical fault analysis because that is most important, and the frequent fault phenomena happens in the power system is of the nature unsymmetrical. So therefore we analyze that, and in that lecture also we discussed how the sequence component is used for analyzing the unsymmetrical fault, and we derived the sequence network for different components of the power system, and also we derived the sequence component network during different kinds of fault particularly at the fault point or the fault location for single phase fault, for single phase to ground fault, for double line fault, for double line to ground fault. So already we covered, and by combining the sequence component network for different components of the power system and the sequence component network at the particularly at the fault point will combine and will get the final network, and by doing that we'll also get the sequence component currents, and from that we'll find the fault current. So already we have discussed this, and in this lecture we'll see the overcurrent protection, which is very important for distribution system particularly, and this overcurrent protection, in fact, it includes many components. First of all we'll see the fuse protection, because fuse also plays very important role in overcurrent protection, and then we'll see the overcurrent protection using the circuit breaker and the overcurrent relay. So particularly we'll see different characteristics of fuse and characteristics of the overcurrent relay. Okay, so let us start. Let us start with the fuse protection. In fact, fuse protection, as I told, fuse protection plays very important role in overcurrent protection. So in this fuse protection we'll cover abnormality and faults. What is abnormality in the system and how it lead to fault, in fact, and then we'll talk about the abnormal state, then the sources of fault current, how the fault current is being provided by different sources, then introduction to fuse, and then we'll talk about the fuse characteristics, then thermal characteristics of the fuse and interrupting characteristics of fuse, and let us see the abnormal state. Okay, so what is abnormal state? Okay, so let us see what it pertains to the deviation of, in fact, deviation from the rated current. Okay, so you should note it down. It is actually, in fact, the deviation from the rated operating point. Okay, that we call abnormal state. Then operation in this state for a long time is actually not very good, so it lead to the damage of the equipment. Okay, then it is also unsafe to operate in this region, because sometimes it leads to fault in the system and leads to damage of the equipment. Now we can see here that, erase it, and you can see here how from normal or healthy state we achieve the abnormal state or the faulty state, then it leads to the permanent fault and we need to isolate the equipment. Here we can see here when the system is under normal condition, we can say it is in healthy state, right? And some abnormality happens, it will go to the abnormal state, and always it is there. If the operating personnel take action, then from abnormal state we can achieve the healthy state, or else it will lead to the faulty state. Okay, so from abnormal state will again it will lead to faulty state, and also faulty state can be achieved directly from the normal or healthy state because of the fault in the system. And from faulty state, if the fault is temporary, then obviously it will achieve the normal or healthy state. Therefore we have the reclosing as a reclosing approach. Always we have, when as soon as the fault happens, the reclosure of the circuit breaker takes place. So it happens for transmission system, it happens once, and for distribution system it may be twice or thrice it happens, the reclosing of the circuit, because sometimes the fault is temporary, and therefore because of the temporary nature of the fault, we can again achieve the normal or healthy state easily, right? Okay, so then we'll see the then from faulty state, if it becomes permanent fault, right? If it's a permanent fault, then obviously we need to isolate the equipment in order to restore the system to the normal or healthy state. So we'll isolate the faulty equipment or faulty elements from the system, and then it will achieve the restorative state. From restorative state, it will achieve the normal or healthy state. Okay, this is the cycle how it happens, from normal state to faulty state, and from faulty state to restorative state, from restorative state to normal or healthy state. Okay, so what is the source of fault current? Let us see. In a radial system with single source, the magnitude of the fault current depends upon the following. We can see generally the distribution system is radial. So radial means the source is the one substation which is providing the radial feeder in the distribution network, and generally the source is the main contributor for the fault current. Suppose the fault happens in the distribution network, right? So we can see here, let us draw it. Suppose this is the source which is feeding a long feeder, right, having different, okay, long feeder. Now suppose the fault happens somewhere at this point, right? So then obviously if the fault happens here, fault location, then obviously the source provides the fault current, right? Okay, then the transformer impedance also plays important role in the fault current, because based on the transformer current, the substation, it is your substation transformer current, the fault current magnitude is decided. And also the motor contribution, if sometime we use the synchronous motors in the industrial utilities, and they are directly connected to the distribution feeder, then this also plays very important role in fault current contribution. Then distance of the fault from the source, okay, so it also plays important role in the fault current, right? So distance of the fault, we can see here, if the fault is at this location, right, so the magnitude of the fault current will vary if the fault location is at this point, right? Let us say this is F1 and F2. If F2 is larger distance from the source than F1, then obviously the fault current for F1 will be greater as compared to F2. Okay. So it also plays important role. Then the transformer short circuit current. that is the short circuit current level of the transformer also plays important role. What is that short circuit current of the transformer? So if we'll define ISC as the short circuit current of the transformer, then it can be defined as the transformer full load current into 100 by percentage Z. How we got this formula? Let us derive it. Okay. So transformer full load current, I can write it as equal to IFL into 100 by percentage Z. Okay. So IFL is your let it be IFL, and into 100 by percentage Z, I can write it as uh, ZB, that is Z base, sorry, it will be Z actual by Z base into 100, that is the percentage Z. Now 100 will cancel out, now we'll get IFL into ZB by Z. Okay. So IFL is the full load current, that means it is your rated current, right? Okay. So I can write ZB as B rated by I rated, right? So your I rated will get cancelled out. Okay. Then I will get V rated by Z. Z is the transformer impedance. So V rated by Z will give nothing but it is equal to the short circuit current of the transformer. Okay. Short circuit current therefore can always be defined if we know the full load current. If we know the full load current, we can find the short circuit current just by dividing percentage impedance and multiplying 100, we'll get the short circuit current of a transformer. So this also plays important role, as I told before. It plays important role in the contribution of the fault current. Okay. Let us give an introduction to the fuse. Let us talk about the fuse. A fuse is a device that opens a circuit with a fusible part, okay, which is heated and severed by the current flowing through it. Its operation involves two phases. In fact, we use fuse at every part. In our household equipment also the fuses are embedded, even in the fridge, in the TV, in the PCs, in the whatever equipment we see, we can find a fuse inside it, because fuse plays very important role in protecting the device. If the device is getting earth sometime because of the insulation failure, then it plays very important role in tripping the fuse. The equipment is being protected, right? And also we have seen the fuse in the household main source, where the main source is connected to the household. So therefore fuse is very important in protecting all the equipment in the household. And similarly the fuses are used in the distribution circuit as well for overcurrent protection, right? So in the fuse has a fusible part. The fusible part means we call it fuse wire generally, fuse conductor, right? As soon as high current flows through the fuse wire, it gets melts and it's severed, right? So therefore it opens, and its operation involves two phases, right? Here it is mentioned two phases. One is the melting of the fuse element when the current has large enough magnitude. So the fuse element melts because of the high current. Because of the high current, the heat is produced, right? We know the I square R. Because of the I square R, the heat is produced in the fuse element and it melts, right? That is the melting part of the fuse. And second part is your current interruption. Okay. As soon as the fuse element is melted, it is the current is not interrupted because of the arc. Okay, so the current is interrupted when the arc stock because of the deionization phenomena. Because of the deionization phenomena, the arc becomes stuck. At that time, only the current becomes interrupted. Okay, we can see here the use of fuse at various parts of the distribution network. For each feeder, we use fuses, right? Okay. So therefore, as soon as the fault happens at any point of the network, what happens? The fuse get melted and it protects or it isolates the faulty part of the system. Okay, this is the phenomena happens in the fuse. Let us see the fuse characteristics. So the fuse has two characteristics. One is your thermal characteristic, which is consisting of current rating and the melting characteristics, and another characteristic is your interrupting characteristic, right? So for interrupting characteristic, we consider voltage rating and the interrupting rating. Okay, so these will be uh, further studied. We can see here. First, let us see the thermal characteristic. What is thermal characteristic? The melting time of fuse is inversely proportional to the square of the magnitude of the current. So it has been found experimentally that the melting time, whatever time it takes to melt the fuse element, it is inversely proportional to the square of the magnitude of the current. Okay, that means your melting time, if I'll say TO, okay, so let's say T of rating or T simply. So T will be inversely proportional to your square of the current. Okay, and this relationship is given by its melting time current characteristics. So this is called the melting time current characteristics. So this is the time current characteristics, and because of the melting it happens, so therefore the name is melting time current characteristics. So fuse has very inverse time current characteristics. So this time current characteristic, in fact, known as in the literature, it is known as very inverse characteristics. Okay, very inverse characteristics. Very inverse characteristics means that the slope is very stiff. Okay, so we can see the characteristic here. It is really very inverse, right? So it is suddenly as the current increases, the time required to melt is very less. Okay, so it is in terms of millisecond. So we can see here the characteristic for different current rating of the fuse element is plotted here, right? For 20 ampere, for 30 ampere, for 50 ampere, 75, 100, 150, 200. For all these current ratings, the characteristic has been plotted between time and current, and it is found that the characteristic is really, in fact, very inverse, right, in nature. The slope is very stiff. As soon as the current becomes higher, the time taken for melting the element is very, very less. Okay, next is your interrupting characteristics. So interrupting characteristic is nothing but the time taken by the fuse element, or the after the melting, time taken by the arc to be stuck because of the deionization. So during arcing period, the fuse must withstand the transient voltage condition, right? So this transient voltage condition in fact happens because of the inductive element in the circuit. Okay, and steady state recovery of the voltage. So because of the stored energy in the inductive element of the power system, for large currents, the arcing time is larger. Okay, when the large current flows, the arcing time is large. Okay, so addition of melting time and arcing time gives us the total clearing time. Okay, so that is the melting time. You can say the melting time plus arcing time is the total clearing time. So this gives us the total clearing time of the fault. So total clearing curve TCC gives this information. So we can see the characteristics. So these characteristics are used to coordinate fuse with overcurrent relay. Okay, to coordinate the fuse with overcurrent relay, this total current characteristic or total clearing curve is very, very important. It plays very important role, okay, for this. So voltage rating of a fuse is the highest voltage at which fuse is designed to operate. So for different voltage rating, the fuse is also designed. We can see here, right, for different voltage rating, the fuse, the total clearing time, total clearing curve is plotted here, right, for different voltage rating, 20, 30, right. So that means, so 20 kilovolt, 30 kilovolt, 50 kilovolt, right, it is designed for all different types of voltage rating, because the transient voltage is very high during the melting. When the fuse melts, the transient voltage is produced because of the inductive element, and the transient voltage is very high, in fact in the range of kilovolt. And for different rating of the voltage, the plots are here, and this curve is known as your total clearing curve, right? It's total clearing curve. Okay. So these curves are plays very important role during the coordination of the relay with the fuse in the distribution system. Very, very important. So let us come to the relay. Now the oldest relay we have is thermal relay, and very ancient relay, and how it operates. Let us see how it operates in fact. So thermal relay, basically when the current flows in the relay, it has two strips of metal. We can see here it has two strips of metal. The upper strip is having the low coefficient of expansion, okay, and the lower strip is having the high coefficient of expansion. That means when the current is flowing through this uh, this relay, that means because of the induction, because the current is flowing in fact in this circuit, right, and because of induction, as the eddy current is flowing through this metal, right, through these two metal strips. One is having low coefficient of expansion and other one is having high coefficient of expansion, and as soon as this, because of these eddy currents, it gets heated, and because of the heating, the lower part of the lower element, that is AB, the lower element, it gets expanded more as compared to the upper part of the strip. So upper part of the strip is having low coefficient of expansion, so it expands less. So as the lower part expands more, therefore it gets curved, right? So as soon as it becomes curved in nature, so this strip contacts the join, right? So you can see here in the next figure, right? So here the lower part gets more expanded, and the upper part gets less expansion, therefore it becomes curved, right? In nature it becomes curved, and as it becomes curved, the trip contacts get the trip contacts actually the trip contacts get connection, that both the contacts they connected together, right? Okay, this is the original condition. This is after high current flows in the circuit. Because of the high current, it produces eddy current in the metal, and because of that it gets expanded, the lower part, and it becomes curved, and the trip contact becomes connected together, it becomes joined, and it gives signal to the circuit breaker for tripping, CV trip. Okay, so this is your thermal relay, and this was very ancient, and nowadays in fact we are using the electromechanical relay or the static relays or the numerical relays. So let us talk about overcurrent relay. The principles of overcurrent protection we'll talk about in this series, in this part. Then we'll talk limitations of fuse, why overcurrent relay is preferred over the fuse. In fact, fuse also gives the protection in the distribution system. So why then a fuse is not sufficient? Why overcurrent relay is preferred over fuse? Then algorithm for overcurrent relay, we'll talk about algorithm, a simple algorithm, which is in fact the basis by which the overcurrent relays are designed. Then we'll see the time multiplier setting. This plays very important role. We'll talk about this, how it plays important role in setting the delays in overcurrent relay. Then we'll talk about the classification of overcurrent relay. In classification, we'll see the lack of coordination problem, then IEEE standard equations. Okay, then we'll talk about the IEEE standard equations, the overcurrent relay. Okay, so let us talk about this. Then we'll talk about the pickup current setting, and in this we'll see the guidelines for pickup current setting. Then primary and backup relays, we'll talk about this. Then the setting and coordination. Okay, all these things we'll cover in the overcurrent relay, this topic. What is the limitation? What are the limitations of a fuse? It is difficult to control the time to trip. Really, in fuse, it is difficult to control the time, because in case of overcurrent relay, we can set the time, and exactly with that particular time delay, it will trip the circuit. And it is really very helpful when the time delay is being used. This makes primary and backup relay coordination very difficult. So therefore, when we discussed in the previous classes that how backup relay plays important role in protecting the circuits, because when the primary relay fails, in fact backup relay is activated and it takes action. Therefore, certain time delay is required for the backup relay to activate, because it operates after the primary relay fails. Okay, once fuse melts, it has to be replaced for re-energization of the equipment. So this is another disadvantage or limitation of the fuse, because once the fuse melts, already we saw many times, sometimes the fuse melts for our computer, for our many equipment, and sometimes in our household also we have to replace the fuse, right? But in case of overcurrent relay, it doesn't happen so. Thus, it is difficult to have remote operation. So, it is difficult, therefore, to have remote operation, because we need to go personally to replace the fuse element. Let us see the algorithm, which is the basis for the overcurrent relay operation. We can see first step is to set the reference or the threshold for discriminating the overcurrent. So that we call the I reference. Okay, that is I reference. So it is very important to select the threshold value for discriminating the overcurrent. Then it measures the device current, and then it compares, right? Then it computes the ratio of absolute I by I reference, which is known as the clock setting multiplier. In short form, we call PSM. So we'll use this term PSM frequently. Please remember this. This is clock setting multiplier. Then the device trips if the PSM is above the threshold. So whatever threshold we have set, if PSM is greater. So for PSM also we put some threshold, right? So then when the PSM is above the threshold, then it trips. So this is the simple algorithm for overcurrent relay. We can see here how it plays very important role, right? We can see here we read the device current, right? Read the device current. Then the device current is being compared with the threshold current, that is the reference current. Then whatever difference we get here, delta, in terms of delta, we call it delta, right? And then it checks the sign of delta, whether delta is positive or negative. If it is positive, it has separate loop. If it is negative, it has separate loop. If it is positive, then the timer gets on. Then it checks whether the timer is on or not. If the timer is on, let us say yes, the timer is on, then it will check for the counter. If the counter is at 0, if the counter is at 0, then it will trip because it gives the time. So that means the time is set and the time becomes 0, and therefore it gives a trip signal to the circuit breaker, and then again next sample is compared. Next current sample is compared, or it is read by the device. Okay. So if it is no, if the timer is not on, then compute the trip time for the relay. Then we need to compute the trip time for the relay and set down the counter. The counter should be set down. Then it goes to again reading the current, right? Similarly here, if it becomes no, the counter is not 0, then it decrements the counter, right? Then it again reads the current sample, in fact, right? In fact, we get the sample, current sample from this current in the sampling form, right? Okay. So if your sign is negative, then the counter is, if it will check if the counter is greater than 0. If it is yes, then it will decrement the counter. Then it will again check the next sample. Then if it is no, then also it goes for checking the next sample. So this is very simple algorithm which is used in overcurrent relay. In fact, in the numerical relay, this is being used. Okay, so we'll talk about the electromechanical relay also in the future classes. So this is the algorithm, basic algorithm used in the numerical relays. Let us talk about the time multiplier setting. What is in fact time multiplier setting? So overcurrent relays normally play the dual roles of primary and backup protection, right? So both it plays it acts as primary relay for the nearest fault location, if and sometimes it acts as backup relay for the distant fault location, right? So therefore it plays the dual role of primary and back. So one relay can act as primary relay for certain faults, and it acts as backup protection for other faults, right? So therefore backup action requires a wait state. Wait state means delay. Okay, and by providing the additional setting feature of the TMS, this can be achieved. So this can be achieved by the feature of, we call it TMS. TMS is time multiplier setting, right? We'll see what is this. This is time multiplier setting, and because of this time multiplier setting, this delay or this wait state can be achieved, right? So TMS is defined as the ratio of T by Tm, right? What is T? Where T is the desired relay operating time, that is the time we required. That means we desire to set the time, right? So that desired relay operating time is T for a given PSM. And what is Tm? Tm is the corresponding operating time for that particular PSM when TMS equal to 1. Okay, that is at TMS equal to 1, what will be the operating time for the desired PSM is known as Tm, right? And T is your desired operating time. So that gives us the TMS, right? So TMS is T by Tm. Okay, so therefore your relay operating time can be varied by varying the TMS setting. So your relay operating time will vary by just varying the TMS setting. We can get different time setting for the relay. So let us consider this example. This is a feeder illustration, in fact. So this is a radial distribution feeder, and it is having three relays, R1, R2, then R3, right? And if the fault is happening here at this location, okay, let us say this is F, location F, then R1 will act as the primary relay for this fault. And R2, R3, they will act as the backup relays. And if the fault is here sometime, right, then your R2 will act as primary relay for this fault, and R3 will act as backup protection for this fault. Okay, so this is how we decide, and we can see now the characteristic when the TMS is set at different values, how the characteristic in fact looks like, right? We can see here the relay operating time is plotted for different values of PSM. PSM is your clock setting multiplier. Okay, and the curve, the relay characteristic, the time current characteristic has been plotted for different values of TMS. So for TMS equal to 1, the curve is here, and if we'll change the TMS, suppose we set the TMS at equal to 2, now the characteristic becomes like this, and suppose we set the TMS at 0.5, the characteristic becomes look like this. Now let us consider a particular operating point, then we'll see the behavior very nicely. Let us set the PSM at this value. That means your threshold reference current is set at 10 to the power 0.5. Okay. Now at this point, if we'll just make the projection, okay. Sorry. If we'll make the projection, okay. So now the operating point at different TMS will find different operating time. How will bit? You can see when the TMS is 0.5, the operating time is here at 5 seconds. Operating time is 5 seconds, right? And when the TMS is set at 1, then your operating time is here somewhere at 9 seconds. Okay. And when your TMS is 2, right, your operating time becomes somewhere here, it may be around 17 seconds. Okay, so for that means when we are setting the TMS at 2, that means your operating time is increasing, and when your TMS is less, your operating time is less, right? So that is how the TMS plays very important role, in fact, in setting the delay time in the overcurrent relays. Let us see the classification of overcurrent relay. So here, first one is instantaneous relay. This classification is based on the operation. So the instantaneous relay, so its action is very fast. Instantaneous relay means there is no time delay. So it has only pickup setting, right? So therefore, only pickup setting, no time delay setting, right? So therefore, its action is very fast. It doesn't have any TMS setting, obviously. This relay is not suitable for backup protection. Therefore, this kind of relay is not used for backup protection schemes. And second type of classification is your time delayed definite time relay. Time delayed definite time relay, as the name suggests, the time delay is there, but the time delay is definite time. We can set it definite time delay in that relay, right? So it can be adjusted to issue trip decision after a specified delay, obviously, right? This delay is independent of the PSM value, independent of whether your current magnitude is higher and higher, it is increasing. Suppose for 100 ampere it is same, for 1000 ampere the delay is same. So therefore it is not known as definite time delay. definite time relay, right? The delay is there, but it is definite, irrespective of the PSM value, clock setting multiplier. Clock setting multiplier is based on the current magnitude. So it is independent of the PSM value. It has both time setting and pickup setting. So it has both the time setting and the pickup setting. So time setting is pickup setting, we give whatever value we want, and time setting is whatever we give the time setting, it is fixed. It will not change based on the current value. So it is used for short length feeders generally. It is not used for long length feeders. Okay, so let us see the operation of overcurrent protection using the definite time relay, how it behaves. So you can see here one feeder that is connected with different loads, different load currents, right? And we have three relays here, R1, R2, R3. Now we need to set the values of R1, R2, R3. So R1, obviously it will become instantaneous relay, because R1 will, as soon as there is overcurrent, the current goes beyond the threshold value, R1 will trip immediately, right? Okay, when the fault is somewhere here, if here the fault, right? So R1 becomes immediately tripped, okay, and without any intentional time delay. Then R2 has to coordinate with R1, and its operation is delayed by CTI. CTI means your coordination time interval. So CTI meaning CTI is coordination time interval. Time interval. Okay, so that is called CTI. So it should be delayed by CTI, and that CTI here it is represented as this green hatching is the CTI for relay R2. Okay, now R3 has to back up R2, and it is again time delayed by one more CTI, right? So therefore R3 is hatched in blue, and this is the CTI for R3, and this is the CTI for R2. Okay, so they both will act. So R2 will back up R1 and R3 will back up R2. So how it happens that sometime the coordination becomes uh, it doesn't coordinate, it unable to, the definite time relay doesn't unable to coordinate with fuse. Okay, let us see it. Lack of coordination between fuse and definite time relay. So let us say we have a relay here, here R1, and which is giving backup to this fuse. This fuse is here. This fuse which is protecting any kind of fault beyond X, right? Let us say the fault is at bus B, and the fuse will act as the primary protection for fault at bus B, and this relay R1 will act as a backup for this fuse. Okay, if the fuse something happens, the fuse doesn't work, then R1 will give protection, or it will give the backup. How there is a coordination mismatch, let us see. Now, if we'll plot the operating characteristic of fuse and relay both, then the fuse characteristic is this. This is your fuse characteristic, right? Definite time relay characteristic. And sorry, this is the fuse characteristic. And the definite time relay characteristic is like a straight line. We can see here, right? This is your definite time relay characteristic. And the threshold is set at this point, I reference, right? And that also known as IFB. So now the definite time relay R1 has to back up the fuse. Let us see how it will work. So after the point X, the relay acts faster than the fuse. So we can see here B and below this point. So this point, this up to this. Okay. So your coordination is very satisfactory, but below this current, the coordination doesn't satisfy, because you can see here, as soon as there is a fault beyond this point, okay, so now what happens, this is actually critical point, right? So now beyond this point the fuse operates first, then your relay operates, right? The coordination is satisfactory. But below this point, right, below this point what happens, your relay operates first, faster than the fuse, right? Because it is based on the operating characteristic of the fuse. So this lack of coordination is due to the different characteristic of fuse, and the relay. That because the relay characteristic doesn't match the characteristic of the fuse, so therefore this mismatch in coordination happens. So how to avoid this? This lead to development of inverse characteristic of the overcurrent relay. In fact, this phenomena lead to the development of the inverse characteristic of the overcurrent relay. So gradually the relays were developed having the inverse characteristics. Okay, so let us see then this. So then the inverse definite minimum time relay came into picture. What is this inverse definite minimum time means? Let us see what is this. It is inverse in the initial part. It is in fact the characteristic is inverse in the initial part, and it tends to approach a definite minimum operating time characteristic as the current becomes high. As the current becomes high, it approaches a definite time, right? So as we can see here, this is the most widely used characteristic because this, in fact, this becomes very suitable. It fits with the fuse, it fits with other relays, so therefore this is the most widely used characteristics. Now we can see these curves, IEC curves, right? So this is in fact these are the inverse characteristic. In the initial part we can see their inverse, right? And after, when the current becomes very high, it becomes get stable, or it becomes definite, right? The time of operation gets definite. You can see for different IEC curves, right? So IEC standard equations for inverse characteristics. Let us see the standard equations used, because these standard equations are very important when these are used by the relay manufacturers, and also these are used by the relay users. So this is in fact very helpful, because the standards are, unless the standards are there, it is very difficult to design a protection scheme, right? Because the manufacturer must use these standards to manufacture their relay, and the operators also use these standards to design their protection schemes. So let us consider the standard inverse characteristics. What is a standard inverse characteristic? This is IEC standard, and the relay operating time is given by this equation, that is TMS into 0.14 divided by I by IS. This is nothing but your clock setting multiplier, we call it PSM, right? And PSM to the power 0.02 minus 1. Then another characteristic is your very inverse characteristic, where the equation is similar, but only thing is the coefficients and the power they have changed. TMS multiplied with 13.5 divided by I by IS to the power 1 minus 1. So then extremely inverse characteristic. For extremely inverse characteristic, this is also, the equation is similar, but the power and the coefficients are different. TMS into 80 by I by IS, this is PSM to the power 2 minus 1. So we can see the change in the coefficients, right, or the constants, and the powers also, change in the power here, here and here, right? So therefore we can say that these standards are very much in use by relay manufacturer and the relay users. Another type of standard we see, that is the IEEE standard equations for inverse characteristics. There are a lot of IEEE standards. First one is your moderately inverse standard, which is T operating. The operation time is given by TD, that is time delay, by 7.0515. So all these equations, and these equations are in fact very useful. Similarly, for very inverse, it is the square of the time as the square of the PSM, I by IS, right? And TD by 7 is common for all, that is a time delay. Okay, for all it is same, and only the power and the coefficients are changing. Here we can see for extremely inverse it is same, but the coefficients are different. For US CO8 inverse, it is also square, and for CO inverse it is the power is 0.02, right? So there are many standard equations and standard characteristics. So the manufacturers in fact follow these standards, and the relay users in fact follow these standards. So these are the curves for IEEE standard, different standard characteristics, right? Okay, they are very useful in relay in protection system design. Okay, so we'll stop here, and in the next class also we'll continue this overcurrent protection. So thank you very much for your kind attention. Thanks.